So here's a few notes on the remainder of this chapter, and it has to do with what happens when you run your experiment and you didn't make any obvious screw-ups, you don't seem to be any design problems, but you don't get the result you were expecting. You get a null effect, which means nothing happened. The independent variable had no impact on the dependent variable. Essentially, the study didn't work out the way you thought it would. So this is a null result. The word null means nothing. Okay, zero, zippo. So nothing happened, seemed to have happened. And you look at your design and you think, well, I think I, prevented all those threats to internal validity. I think I did a good study, yet it just didn't work. So now what do we think? Well, there are a few questions to ask at this point. So let me start. I'm just going to look at your chapter and kind of hit a couple of things. One thing might be, well, maybe the measure you used for your dependent variable was not very good. Maybe it was insensitive and it couldn't really capture that thing you were measuring. Maybe the difference is out there, but you just didn't see it in your measure. The questions you asked on your survey just didn't really tap into the thing that you were trying to tap into. That could be. Let's see, some sort of specific case of measures that aren't sensitive enough or are too sensitive are things called a ceiling effect and a floor effect. And a ceiling effect, it's something where people basically max out the options on your survey or your measure. Let's see, I think I have an example in a homework where it says, what if I'm surveying same-sex couples and heterosexual couples on marriage happiness, satisfaction. And I have a scale from like 1 to 3. And pretty much most people are putting 2s and 3s, or there's no significant difference in the measure, the average satisfaction scale between the two groups. Well, if it's like unsatisfied, neutral, satisfied, and people put 3, that wouldn't maybe catch any specific difference in the groups. Everyone's just kind of maxing out. If I, write an exam for a class and my goal is to find out what did you learn and sort of what are the differences between students and how much they know and what they learn, but I write this really easy test and everybody gets 100%. Well, from that, in the class, there really is going to be differences in how much different students know. There are going to be people that really know everything they were supposed to learn, some that got most of it, some that got a little, and some that life happened and they didn't learn anything that week, right? So there is real variation out there. But if the test I write is so easy that everyone gets 100%, well, everyone's hitting the ceiling of my measure, and I'm basically missing the actual variation in what you know. Ceiling effect. It's almost like if we all wanted to weigh ourselves and get the class average weight, but all we had was one of those vegetable scales from the produce aisle. So we all climb in the little basket one at a time, and it only goes up to 5 pounds. We're like, oh, we all weigh 5 pounds. Woo. That's a ceiling effect. We've just maxed out what our scale is. I'll give you one other real life example. I used to work in a lab with monkeys and they tested memory. And we wanted to compare the monkeys to college students. And so it was spatial memory, and there were like 20 different spots on this board, and you had to remember where the last disc was and the new one is and all that. Well, the monkeys, they get up to like 3, 4, 5, they start making mistakes. The college students were doing a lot better. And it was a gender thing, actually, because the female monkeys were doing better than the male monkeys. And we thought, oh, I wonder if there's something in humans. But the thing is, in both groups, everybody was getting really high scores, the average of 17, 18 out of 20. And the question was, so there was no difference, it was a null thing. The question was, well, is that because there's no difference in the human spatial memory? Or was it because the task with only 20 spots on the board was actually pretty easy and everybody could just do it? So maybe there is differences that we weren't capturing from that measure, and that would be a ceiling effect. Floor effect would be the opposite, where the measure is so hard that it doesn't register the true variation. So that would be like, instead of giving a super easy test, I gave you an exam that was so hard that everybody failed it. Now, again, I'm just like, oh, none of you learned anything. Well, no, there are true differences in what you learned, but I'm missing the variation because my test is so hard. You guys can't even get on the floor of the test. You can't even get the minimum score. So you're under the floor of the measure. So if we want to use the weight example again, they're like, oh, we're going to get the class average and weight. but all we have is this scale that they use for semi-trucks, so step on it one at a time. It's like, you weigh 0, you haven't even tripped the scale. That's a floor effect. You can't even get onto the measurement because it's so hard, and it can't detect you. So those are some specific examples of insensitive measures, or things that just aren't getting what it needs to get. Okay, I want to move on now. Another big problem is in any group, you know, we've got our 2 groups at least, maybe we have more groups, and we're measuring something about you at the end of the study. Well, when I measure different people, there's going to be what's called random error. And most of random error, your book calls it unsystematic variance. Random error, same thing. Most of that comes from individual differences. So I'll give you an exam. Your differences in test scores, I hope, and usually a big part of why one person gets an A on my exam and one person gets a C has to do with differences in what they know about the material. I mean, that's kind of like my independent variable. That's like what I really, or dependent variable, that's what I really want to measure. But you can appreciate that there's going to be part of their grades that is due to other things. There's to be one person that did not get as much sleep. One person who's like all stressed out because they just got dumped by their girlfriend and they're all, and they can't concentrate. One person who maybe, you know, I wrote the question using a word that they don't really know that well, and that ever happens, ask me. But, you know, they're a little confused by how they read the question, or they read the question too fast, and they thought they understood what they did, but they should have read it more carefully. And so there's all these things that kind of come into your exam score that don't really have anything to do with what you know. That's the random error, okay? Maybe there was someone next to you just sniffling the whole time and being really distracting, or they smelled, or you had a cold and you just couldn't focus. Those things will contribute to your exam score, and they aren't what I'm trying to measure. That's, in that sense, it's actually measurement error. So they will affect things, and to the extent that there's a lot of that going on, there could be so much within group variation, individual differences, that it kind of overwhelms the thing I'm trying to detect, how much you know. A great way to think about random error, this unsystematic variance, is to think of like a radio station. When you're, you know, looking for a radio station and you get static, if you guys ever actually listen to the radio anymore, you know, if you're not quite on the station or it doesn't come through well on your car, you get the static. Now the music or the talking, the song you're supposed to hear, that's the signal. So in an experiment, the signal is the impact from the independent variable. It's the thing we're trying to detect. But there could be all this background noise, all this static that makes it hard to hear that song, to hear the signal. So if we have a lot of random variation, unsystematic variance in our group, in our dependent variable, it may basically overwhelm the actual impact of the independent variable that we're trying to detect. Now, your book talks about some ways to deal with this. Maybe you can do a slightly different design, like a repeated measures. That'd be great. Sometimes just upping the sample size can help with that. Another way is take that individual variation, individual differences, because those are the biggest, that's the biggest source of the random error. I don't think your book talks about this, but if you could make your people less different from each other, what if you reduce the individual differences by sampling people that are similar to each other? Here's an example. A lot of times in medical research, when they're doing stuff to begin with, they'll only study males. Now, there's a reason for that. Because depending on what they're doing, the claim has always been, well, the female cycle, the monthly cycle, will change hormone levels vary more, maybe in females than in males. So we want to just make sure this drug works, or make sure what we're looking at actually works, and then we'll deal with it with females. It was probably less noble excuse, you know, back then. I mean, they used to do medical research on like healthy, strapping 20-year-old Navy SEALs, you know, and they'd like give them, you know, like measure hurt and stuff, and, you know, get all this medical data. And these guys are in the Army or the Navy, and they're kind of easy to sign up for studies because they have to kind of do what they're told. It's not really allowed anymore. And they get this data, and then they realize, oh, but maybe they, they're all very similar, so it made a nice clean study, got clean data, not a ton of individual variation in their physical, state. They're all in really great shape. But so they could find their difference. Of course, then the issue comes, what about external validity? I mean, for years and years and years, we knew all this stuff about heart attacks and heart disease, and then people are like, oh, you know what? When you look at women, it's really different, okay? So, but in a study, if we want to make sure we can find what we're looking for, we might start out and go, well, let's get just people that are real similar and there's not as much variability. So I might have criteria for people. In that memory study, actually, we did rule out people. We said you couldn't be on birth control. Wait, yeah, you could, but we had to know if you're on birth control because that could affect the memory. Or the cycle, where you were in the cycle could affect memory. We said you couldn't be on certain prescriptions. You couldn't have had a head injury. There were things that ruled people out from even being in the study because we wanted to contain a little bit the individual variation that we knew could mess it up. And then if we could find our effect, well, then we could relax that later. Now, I don't think your book talks about this particular approach, and it would reduce your external validity if you're making your sample more homogeneous, more similar to each other. But sometimes that's a way to kind of reduce the noise. All right, situation noise, you can read about that. Your book's going to talk about power. All of these things, when a study doesn't work or it comes out, it's not significant. What we say is you may not have power. Now, power has a lot of things that go into it. We're actually going to get into that more when we do the basic statistics next week. So we'll kick the can on that right now. So these are the things people ask when they get a null result. They don't see their significant difference. Now, one real possibility is there is no difference. Your independent variable does not have an effect on this dependent variable. That's a very real thing. And it's important to know that. Now, we don't give up on one study. If it doesn't work out, we kind of tweak it a little bit, try some of these things, maybe change the design, do it again. But if you do it a few times and it's just not there, well, you might just say, it's not there. There is no difference here. Okay, well, and that's interesting. Now, people are not as likely to publish null results because you like to publish things when we say, hey, we found this causes this. When we go, oh, this apparently doesn't have anything to do with each other, it's not quite as exciting. It's a little bit harder to get published, and that's unfortunate. Sometimes it's called the file drawer effect because people like, well, we'll just file this and we won't publish it or mention it to anybody. Now, sometimes people do, but the danger there too is like if you tried something and it didn't work and you're like, if nobody knows about it, someone else might come up with the idea, hey, let's try this, and they don't realize someone else tried it and it didn't work. So that's a tough thing in science, but it's just this thing that we have to be aware of. And it just has to do with publishing pressures and things, and journals like to publish things that are exciting. There's limited space. But all right, I think that'll do it. So if you do read through that, there's some details in here that aren't going to be quite as important for us, but just give a good read through, and then you can use the quiz as sort of a guide for the kinds of things I might want you to know about the rest of this chapter.